Now we'll study ratio estimation more formally. We'll use x to denote a scalar x variable, a scalar auxiliary variable. Oops. And there are two conditions about this auxiliary variable. First, it should be positively correlated with the study variable y. Otherwise, the ratio estimation does not help. Second, the population mean of the total of the auxiliary variable should be known. We never know this information from the sample, so it should come from an external source. The idea for ratio estimation is to use information x bar u, the external information, to improve y bar. We can use ratio estimator to estimate the population mean or population total. For the mean estimation, we use this formula, and so this is R. And so R is the ratio. We can call it ratio factor. For total estimation, we apply the same ratio. So turns out that it's the same ratio because we have 1 over n here. Then it's a mean. So cancels. So this is we have the same one. So R applied to the unbiased estimator of the total. Okay. So the ratio estimator can be constructed from other sampling designs, but we'll consider simple random sampling design only in this class. Now, let's study the main properties of the ratio estimator. So the first part is an algebraic property which has nothing to do with the statistics. It's just a purely mathematical property. The first property is that ratio estimator is a weighted mean of the sample observations. It's a weighted combination of the sample observations. So you can, because why? Because this one is R y bar, right? So that is the, and so by the way, oops. Y bar is just the sample mean, so it should be I. So that means if you write it this way, Wi yi, that means Wi is equal to 1 over n R. Okay. So and this is actually random. This factor is random. Why? Because the R is x bar u divided by x bar. So this guy is fixed, right? But this guy, denominator, is random. If you repeat your sampling, the denominator will change over samples. So with the samples. So if we apply this weight to, so by the way, if you apply this weight, okay, to x, okay, then what? Then okay, so if you see, let me write it in red color. Wi xi is 1 over n R times xi. So that is R times x bar, right? And R is actually x bar u divided by x bar, so times x bar. So it cancels to each other. So you end up getting okay. So you get, so it provide so the left side is an estimator, right? You compute something from the sample, but the right side is actually population quantity. So that is nice. If x bar is sample mean of x is less than population mean of x, then the by definition ratio is greater than 1. So that means the ratio estimator is greater than the sample mean, which is good because why? Because we know that the sample happen to be smaller samples than the mean, right? So that gives some accuracy improvement. Here's an illustration to understand using an example. So so the sample is we have a we have a 20. If you count these dots, you have 20 of them. So these are the sample, and the red line represent the true line, right? I mean, so this is the red. Now the population mean of x. So the point is that you have a x bar u, which is 5. So this is x bar u. So this x bar u is the true population mean of x, but in the sampling, your sample has a 5.33. So that means what? That means your sample is somehow bigger. So this is sample mean, right? So your sample mean of x is slightly bigger than the population mean. So the ratio is x bar u divided by x bar, right? So that is 5 divided by 5.33. So which is 0.938. So the ratio is 5.938. So you apply your ratio estimator. So this is your y bar, and then you can actually apply 0.938 y bar, and that is actually this is 4.27. So that is your regression estimator is 4.00. If you do computation, then you end up getting this. So your ratio estimator is really close to the population mean. So the population mean is 4. This one is 4.0056. So that this is 4.2927. Okay. So this one is the second case. So the ratio sample mean is greater than the population mean of x. So the ratio is less than 1. So you kind of reduce the sample mean, original sample mean of y, by ratio r, and that it should give you a better estimate. Okay.